These are the 3.2 part 1 notes, and we're going to start looking at least squares regression lines. So first we have the concept of a regression line. And a regression line is a line that describes how a response variable y changes as in the explanatory variable x changes. And we often use a regression line to predict the value of y for a given value of x. And I've got an example of a best fitting regression line here. I stole this off the internet. I thought it was pretty funny. It's somebody describing their sleep and hours versus their grumpiness, and we can see that every day they figured out how much sleep they got, rated their grumpiness scale, and we can see as they get more sleep they get less grumpy. And we can see that general trend with the scatter plot, and like we learned, the scatter plot is going to have some level of an R value, and that R value is going to determine some level of linear relationship. The closer it is to 1, the more likely we are to say that there is an appropriate linear relationship. And we don't want to just know whether or not the relationship's linear. We kind of want to have an idea of what that looks like. So we have the best fit line, and we put the best fit line through our scatter plots to figure out what that is. Now, how do we figure out what the best fit line is? What is the best fit line? And then how do we interpret it? So how do we interpret a regression line? So the least squared regression line works off the formula y hat is equal to a plus bx. Now, a is your y-intercept, b is your slope, x represents the explanatory variable, and then y hat represents the expected x value. Now this looks a lot like y equals mx plus b. This essentially is y equals mx plus b, but we put different symbols on it to establish the fact that we're not working with a pure linear relationship here. We're working with something that looks very, very linear. And since it looks very linear, we're going to go ahead and give it a form of a linear equation. We're going to write out this, what this means. Your y-intercept represents what would happen if your explanatory variable was zero. So if I'm talking about something like the weight at number of months, I could say at 0 months, which means that that's the weight things are born at, if I'm talking about an animal. If I'm talking about something like position versus time, whereas your expected position versus time statistically, then I'm going to be looking at, okay, 0 represents time 0. So there's a variety of things of what that means, but what it means is if we look, in context it has a variety of meanings, but what it means just kind of in raw form is when your explanatory variable is equal to 0, what is the expected y value? Your slope, that's how much it changes. So basically for every time we change our x, how much do we expect our y to change? And your slope can be big, it can be small. Your slope has really no impact on how strong a linear relationship is. You could have a very strong linear relationship with a very small slope. You could have a very weak linear relationship with a big slope. But basically what it's saying is for every x we move horizontally, how much do we expect that y value to change? Do we expect it to go up? And if it's going up as we move to the right, then we have a positive slope. And if it's moving down, if we expect it to move down as we go to the right, we're going to expect a negative slope. So this is all Algebra 1 stuff, things that I know that you guys know how to deal with. We're just applying it in a new scenario. Extrapolation. So extrapolation is the use of a regression line for a prediction far outside the interval value of the explanatory variable x used to obtain the line. And such predictions are often not accurate. So we have explanatory variables, we have regression lines, and usually those regression lines and explanatory variables gives us something within a certain window, a reasonable window. The book used the example of car sales where for a certain amount of mileage on a truck, you're going to see the cost kind of obey a certain regression line. Well, if you get to 300,000 miles, you get something like negative $5,000, where I would have to pay $5,000 for somebody to take the truck off my hands. And that's obviously where the regression line stops kind of making sense. And there's a variety of ways a regression line can stop making sense. So on the left, I've got just this cartoon I found from, I believe it's called XCDB. I don't know. But the cartoonist is from a college really close to where I grew up, so I'm a pretty big fan of him. He was a physics major at Christopher Newport University and started this cartoon. And he does a lot of math and physics-based cartoons. And so he's got this good cartoon here, like My Hobby Extrapolating. So he's made this regression line of number of husbands this woman has yesterday versus today. And if we extrapolate that data, we can see that she'll have 4 dozen husbands halfway into the next month. And so that makes sense if we're using the extrapolation, but honestly, in real life, it doesn't make sense. Now, a really easy example of how extrapolation in like the real world wouldn't make sense is if we're talking about a dog's weight and age in months is measured by this random least squared regression line. Okay, that works right now as they're a puppy and they're growing, but we don't expect a 72-month-old puppy to be much different than a 60-month-old puppy. That's the difference between a 6 and a 5-year-old dog. So if I start plugging in 60 months, 72 months, that's suggesting to me that the dog is still growing at 5 and 6 months, which that doesn't make sense. I'm not going to be able to extrapolate that. This works for a given time value, but then there's a certain point where that time value is going to cut off. There's plenty of other things that we can look at extrapolation with, but a lot of them are going to come in like cost of products, weight of animals, things of that nature. It's like another idea of not like just off the top of my head, number of minutes studying versus your grade on the exam could probably be represented by some linear regression line. We can make up some regression line to make up that relationship. However, there's going to be a certain point where it's like, okay, if you spend 100 minutes studying, you get 130%. There's a certain point where it no longer makes sense given the scenario of what your actual grade is versus the amount of time you spend studying. That regression line is going to end up giving you values that make no sense in context. So we've got a brief check for understanding here. So we've got some data were collected on the weight of a male white laboratory rat for 25 weeks after its birth. A scatter plot of the weight in grams and time since birth shows a fairly strong positive linear relationship. The linear regression line of the equation, the expected weight, is equal to 100 plus 40. And I can even kind of say whenever we see the hat symbol anywhere, that means expected, times the amount of time, and we're basing this off weeks. So what is the slope of the regression line? The slope of the regression line is 40 grams per week. And I can use that based off my explanatory variable and my response variable. This is going into like science and algebra 1. Since weeks is my explanatory and weight is my response, I can say, okay, what we're saying is that every week we measure this rat, it grows an extra 40 grams in weight. And that's what that slope means. What's the y-intercept? The y-intercept is 100 grams, and that 100 grams is its weight at birth. So when it's 0 weeks old, the day it was born at 100 grams. Predict the rat's weight after 16 weeks. So this is where I would just go ahead and say that its expected weight is going to be equal to 100 plus 40 times 16. So give me a second as I pull out my handy dandy calculator. I can do 40 times 16 in my head, I promise you, but it's not always the easiest thing. So that's 100 plus 640. So that means y hat is an expected 740 grams. And then should you use this line to predict the rat's weight at the age of 2 years? Use the equation to make a prediction and think about the reasonableness of this result. So 2 years, that's 52 weeks, that's 104 weeks. So we would be saying 100 grams plus 40 times 104 weeks. So 40 times 104 is 4,1600 plus 100. So we'd be saying that this is 4,260 grams. There are 454 grams in a pound. So this would be saying that we've got a 9.38 pound white lab rat. I don't know the size of white lab rats. I've seen like I've seen all the memes of like rats that you'll find in sewers and things, and they look pretty big. But I'm going to assume that a rat that you would find in a laboratory, like everything that you see in TV shows and cartoons and movies and things like that, kind of show these small little animals. I'm going to guess that a 9-pound lab rat is going to be pretty big. It also just doesn't make sense here. The rat's going to stop growing after a certain point, and I would imagine that it would be before 2 years. It's not like a rat has a lifespan of a dog. and a dog has stopped growing usually about a year and a half. So at some point, this is going to stop making sense. This extrapolation can't keep going. Again, if we somehow had a 4-year-old rat, it would end up weighing like around 20 pounds, and that's where we start getting to a point of ridiculousness. All right, residuals. A residual is the difference between the observed value of the response variable and the value predicted by the regression line. So that is the observed y minus the predicted y, or the actual value minus the expected value. So we've got a regression line here of weight related to height of some animal, or baby or whatever, and we can see all the residuals marked. So these lengths here that occur between the regression line and the actual y value, that's the residual. And we report the residual in terms of what the y value is, because we're talking about the difference in the y value. So here, our residual would be measured in inches, of the difference in inches from the actual value to the predicted value. Everything that occurs below the line is going to have a negative residual. Everything above the line is going to have a positive residual. Because here, above the line means that our actual value is greater than our expected value. Below the line means that our actual value was below the expected value. And knowing the residual is actually really, really important in being able to figure out what the best fit line is. Now, there are a number of ways that we can fit lines to data point, but the way that we're going to be using in this class pretty much the entire year is going to be the least squared regression line. This is the most basic one. This is the one that's the most straightforward. Again, there are other regression lines, but this is the one that is kind of the basics for figuring out how can we make a line fit data? How can we model it versus our data? And I found this visual on the internet to kind of help explain what a least squared regression line is and how it works out. So here, up here to the top left, we can see that we've got two scatter plots, and those scatter plots are the exact same, but I've got two lines that go through it. And we want to ask ourselves, okay, which line is a better fit based on the least squared regression model? Is it the left line or is it the right line? And you might be tempted to say it's the left line. Well, it goes through two of the points, so obviously that's going to be a better fit than the right line. The right line doesn't go through any of the points. It's just kind of there in the center. I don't think that's going to be the correct fit. Well, this actually isn't the case, because what we do is we find our residual, and then we square it. And when you square that residual, you end up creating kind of like this space here. And we can see that represented on this picture down here, is they've taken the distance and they've squared it. And then the entire idea is the best fitting line is going to be the line where these squares add up to the least distance. So here we've got like that square plus that square, so we've got, or least area. We've got these two squares adding up to create some level of area. We've got these three squares adding up to create some level of area. And here there's not a positive or negative value for these squares, because whenever you square a negative residual, you're going to get a positive area. Whenever you square a positive residual, you're going to get a positive area. So it's still just about what has the greatest area. The signs are taken out of this. Now, this is going to be kind of hard to see because they don't give you any actual numbers, but we see that we've got 1, 2, 3 areas here, and we've got 5 areas over there. Well, these 3 areas on the left are actually going to be added up to be greater than the 5 areas on the right. We can kind of see that the size of those boxes are much smaller. We've got two wildly, on the left, we've got really, really large residuals, which are giving us really large area boxes. Those added together are going to create a pretty large area. On the right, we've got much smaller residuals. We have more residuals, but they're smaller, so we create these squares that are smaller. And then when they add them up, the areas get smaller. So it actually ends up being that this is the better model. This would be the line we would use for our least squared regression. Because when we add up the areas of all those boxes, it's going to be smaller than when we add up the area of the boxes on the left-hand side. I realize that's kind of difficult to see, but that's how we go about it. And we're not going to calculate this by hand. We're not going to go through. We're not going to try to figure out a residual distance. they have computer programs that do this. We're going to use our computers, we're going to use our calculators, we're going to plug in the data, and then the data is going to spit out what the least squared regression line is. It's just important that we kind of get a concept for why it works. Now, a residual plot. To explain what a residual plot is, I kind of want to explain a basic property of the least squared. The mean of the least squared residuals is always 0. So that's another good way to tell if a least squared regression line is going to work out. One of the ways that I could have told you that this left line wasn't going to work out is I've got two really, really large positive residuals and only one really, really small negative residual. So overall, the mean of my residuals would have been a positive number, and it would have been a fairly large positive number. Over here, I can see that I've got two positive residuals, and yes, I've got three residuals that, while all together are each smaller than the positive, when we add these up, this is going to end up giving me a mean of roughly 0 residuals, because I'll add a negative plus a negative plus a negative plus a positive plus a positive. So when I add those two positives and those three negatives, it's roughly going to give me something around 0 for my number of residuals. It might give me something a little bit different. It might be a little bit above 0, might be a little bit below 0. At the end of the day, your mean, the average value of your residual is going to be roughly 0. Now, we're going to use this property to help us make a residual plot. We use a horizontal line to represent the mean of the residuals, and we say that's y equals 0. And then we plot the residuals versus the explanatory variable. So our x-axis should not change from our regression line, from our normal scatter plot. But what we are going to change is we're going to shift our y-axis. We're going to change our y-axis from being, the number of the observed value, we're going to change it to our residual value. And this is going to help us determine if a linear model is appropriate. So here I've got two residual plots. All we're looking at is explanatory variables versus response variables. So here, this is something that was on the internet, which you kind of see in your book. It's the Old Faithful eruptions. So we can see here a scatter plot, the amount of time between eruptions, and I'm going to guess that the y-axis is based on the length of the eruption. And we're looking at the residual. So what we're seeing here is just a raw data number of, okay, what does it look like? What were the difference between the actual eruption times versus the expected eruption time based on how long we waited for the eruptions? And what we see here is a random scatter of data. I don't see really any real pattern here. You might be able to make an argument for something, but at the end of the day, I see a lot of values really high, I see a lot of values really low. There's no real linear relationship. It's just all kind of scattered. So I would say that there is a decent chance that this could be modeled linearly. Now, over to our left, I see a residual versus explanatory variable plot. And what I see here is a very clear pattern. I see a very clear curve. It kind of exists everywhere within this, where it goes up, goes back down. It's arcing everywhere. There's a clear arc. It's not, I don't have any values below my mean in the middle. I don't really have any values above my mean to the farthest left and farthest right points. So what I'm going to say here is that I can clearly interpret a leftover pattern is that this is probably not going to be modeled linearly, or it's not the best idea to model it linearly. We could probably still make an attempt at modeling it linearly, but here it's clearly saying like a linear model is off, because when we do the residual versus the explanatory plot, we have a clear pattern, and we don't want any clear pattern. We just want a random grouping of values. So here we've got a brief check of for understanding. We have this residual plot of the body weight of hikers versus the body weight for their backpack. One hiker had a residual weight of nearly 4 pounds. Interpret this value. So what this means is based on the body weight of the hiker, so based on this 165-pound hiker, we expected their backpack weight to be 4 pounds less than what they actually ended up with for a backpack weight. So here we can clearly see that we're talking about the 165-pound hiker. Their actual backpack weight was 35 pounds. So that meant we expected their backpack to be 31 pounds, but they actually had a 35-pound backpack based on the residual line which we would have created there. Now, based on the residual plot, is the linear model appropriate here? I would say yes. This seems like a pretty random scattering of points. I don't see any real pattern. They're above, they're below. There's a certain level here that I would claim that, okay, we have more evidence here that defends using a linear model to make this plot. All right, you guys have a homework assignment tonight. Please reach out to me with any questions or concerns, and have a great night.